So the work problems for chapter 14, I'm trying to get my marker to work here. Okay, there we go. So as always, I want to start off with the credits. So the credits should be given here to Brown and LeMay and also to Zumdahl in their chemistry text, because that's where the bulk of the problems came from, along with Mr. Mack's AP chemistry site, which basically took the problems from Brown and LeMay. So, but anyway, so that's kind of like a double credit. So to Brown and LeMay, and then also occasionally there will be a problem from McMurray and Fay's excellent book on chemistry. Answers are provided by myself. Next slide. Next. Okay, first problem here is very simple. So we have a reaction 4pH3 giving P4 plus 6H2. In a certain experiment over a specific time period, 0.0048 moles is consumed each second. So what are the rates of production of P4 and H2 in this experiment? So I usually don't put the answers on the same slide with the questions, but for some reason I missed this one, so it's actually here. So anyway, we're given that this is what's happening over a period of time in a 2-liter container. Why don't we first of all get it to the units that we're more used to, get it moles per liter per second. So let's just multiply this 0.0048 by 1/2, or divide it by 2 and get it to 0.0024 moles. That would be used up each second in 1 liter. That would give us 0.0024 moles per liter per second. And then we'll use that to work with, and then it's just a stoichiometry problem. So, I mean, the relationship between the pH3 here and the P4 here is that for every 4 pH3s that are broken down, we produce only 1 P4. So the rate for P4 formation would only be 1/4 as much as this. So divide through by 4 and you get 0.0006, or 6 times 10 to the minus 4th moles per liter per second. And then again, stoichiometry for here to here, for every 4 of the pH3s, we produce 6 H2s. So in other words, we produce 3 for every 2 of the H2s. Or you can leave it the way it is and just say 6 per 4. So whatever the rate is for the pH3, you would multiply it by 6/4 to get the rate for the H2. And that would be 0.0036 moles per liter per second, which is rewritten as this. Okay, and just let me just mention this. If you are doing a test and you leave it like that, and if I have the ability to do it, which I would, like on a short answer question, then I will give you credit for it, even though you didn't, because I'm not that worried about whether you write it like that or like that. Okay, next slide. All right, so here we have a reaction of 2NO plus Cl2 gives 2NOCl. It was studied at a certain temperature. The following results were obtained, and here are these results. And so we have here a situation like the one that we looked at in the lecture notes, where we are given these different values at different concentrations at different 4 different runs, and we're supposed to find the rate law. In other words, we need to find the exponents and also the value of the rate constant. So let's look at this. So first of all, when we do the first 2 runs, we're keeping this constant here. The NO is being kept constant. We're doubling Cl2. So the way that you can do that if you want to is you can write 2 here as your base number. And what number do we have to raise 2 to get what happens to the rate? Well, the rate doubles 2. So you could write that as 2 to what power equals 2. And the answer is 1, right? So it's first order. So for the one that we're changing here, which is the Cl2, the reaction order is 1. Now, to do the NO, we have to come down to runs 2 and 3, where we're holding Cl2 constant and we're doubling NO. So again, the base number for NO would be 2. What power do we have to raise 2 to get the corresponding increase in the rate? And the rate here is actually going up by 4. So 2 raised to what power gives you 4? The answer is 2. So this is actually second order in NO. And that's how you do these. So the rate law down here, remember that the rate law is always rate equals some rate constant K times the concentration of one reactant to certain power times the concentration of any other reactants to their power. So in this case, you would write rate equals K times the concentration of NO to the second power times the concentration of Cl2 to the first power, or just leave the 1 out. To get the rate constant, you'll have to use this data that you're given here in the table, and just use that equation that we just said. So for example, and you can use any of these 3 rows, you're going to get the same answer. But for example, if you use row 1, then you would write the rate, which is 0.18 moles per liter per minute, equals some rate constant K, which that's what you're trying to find, times this concentration right here squared, so it would be 0.1 squared times the concentration of the Cl2 to the first power, so times 0.1 to the first power. So that's just going to be 0.1, and then 0.1 times 0.1 is 0.01, and 0.01 times 0.1 is going to be 0.001. So anyway, that's going to be what you're going to get. So it's going to be this rate equals K times 0.001, which it looks like it should be 180. Let's go to the next slide. And it is, actually. So I just kind of skipped down to see if I got it right. Okay, so what this slide is doing is it's just telling you what I just said. So our rate law is rate is K times NO2 squared times Cl2. Note that the reaction is third order overall. If you add the 2 there to the 1 there, you get 3. And then to get the K, you just write this law, and you can rearrange it if you want to get K on one side of the equal sign by itself, and then substitute in from any of the rows above. So you can use the first row or the second row or the third row, or as they're sometimes referred to as the runs. Okay, so let's go to the next slide. All right, another problem, the decomposition of ethanol on alumina. C2H5OH gives C2H4 plus H2O, and it was studied at 600, and we have a clue coming up. Concentration versus time resulted in a straight line. Okay, so this is our first clue. Maybe the only one, but at least we got one. It's zero order. Because whenever you plot concentration versus time and get a straight line, that's a clue that you have a zero order reaction. So the rate law is going to be that rate equals some rate constant K times the reactant here, which is C2H5OH, raised to the 0 power. But C2H5OH raised to the 0 power is just 1. So your rate law will reduce all the way down to just rate equals K times 1, or in other words, rate equals K. So the rate law here will be rate equals K. So, I mean, they didn't ask this, but remember that when you have that kind of a situation, the constant K has to take on all the units that you need. And we always need the same units, moles per liter per second. Okay, the integrated rate law for a zero order reaction is concentration of A sub T, but let's write what it actually is. We only have one reactant here, so let's write it that way. The concentration of C2H5OH, which that's ethanol, at some time t equals minus KT, and then that's going to be plus the concentration of C2H5OH at the beginning, or at the 0 time. So that would be the integrated rate law. You could actually put the K in, but they didn't ask us to do that. The value of the rate constant. Okay, so remember we talked about this. So it's A sub T equals minus KT plus A naught. So the minus K is in the place where the M would be, the slope, in the equation of a straight line. So in other words, the slope equals minus the K, or you could also say the K equals minus the slope. In other words, you could say that the K would be the minus of that number right there. And that number right there is minus 4 times 10 to the minus 5th. So if you just change that from minus to plus, you'd have K. So K would be plus 4 times 10 to the minus 5th moles per liter per second. Notice how easy that was. If you tried to do it the long way, it might be very difficult or impossible. So you'll have to really watch more, I think more so in this chapter than any other chapter. You have to watch for these little clues. So we had a clue here when they told us that when we did concentration versus time, we got a straight line. And then also we remember that M is minus K for zero order. And that's also true for first order. Next problem. Oh, this is the answer. So let's go to the next one. Write the rate laws for the following elementary reaction. Okay, we usually cannot look at a reaction and write the rate law. We cannot use the coefficients of a reaction, and that's talking about the way that they're written in your textbook or in most problems. Unless, the exception to that is unless they actually tell you that these are elementary reactions. And if and only if they tell you that, then you can look at the reaction and you can write the rate law just for that one step. So, I mean, maybe we should rephrase this or put an alternate word here, step, because it's a step in a reaction mechanism. Whereas when you use the word reaction, I mean, it's not incorrect here to say reactions, but it makes it sound like it's an overall reaction, and it's not. This is one step in a reaction, and the same thing for B, C, and D. So here for A, once you know that, it's very simple. You just write rate equals K times whatever the reactants are, and you're done. And if you have more than one of them, then you would write to the second power, but we don't have that. And again, let me remind you that you don't put plus. You're multiplying when you write the rate law. So for A, it's just going to be rate equals K times the concentration of CH3 and C. But for B, it's rate equals K times the concentration of O3 times the concentration of NO, not the concentration of O3 plus the concentration of NO. So you have to watch that, and the reason I keep saying it is because it happens so frequently. And for C, there are two different ways C is written. For the first C, rate equals K times the concentration of O3, and for the second one, it's rate equals K times the concentration of O3 times the concentration of O. And that's enough of that. Let's go on to the next slide. And then the next. The activation energy for the reaction going in this direction for NO2 plus CO is 125 kilojoules per mole. So this distance here is 125 kilojoules per mole of reactant, either reactant, and the delta E for the reaction, in other words, it should be maybe delta H, but okay, so the delta E for the reaction, in other words, the distance from here where you started to here where you end up as product is 216 kilojoules, which is written as a negative because it's exothermic. So you're giving off this energy, so you're ending up lower than you started with. So this will be exothermic. Your products will be more stable than your reactants. If you wanted to make it go in the reverse direction, therefore, you would have to add energy to it, like a heck of a lot of energy. Because its natural state is that it's not going to want to go backwards. Once it gets here, it's stable. It just wants to stay there. So to get it to come out, it's like in a roulette wheel. When you put the ball into the roulette wheel and spin the roulette wheel, the ball will go around and around. Eventually, it'll wind up dropping down to the lowest point available to it, which is going to be one of those slots. If you want to make it come out of the slot, you've got to reach down and actually physically pick it up, because it won't come out on its own, basically. So anyway, that's what we have here. But they're asking us, what if you did want to put energy into it and make it go in this direction? So how much energy would you have to put into it? Well, you'd have to replace the 216 kilojoules per mole that you had given off at the end of the reaction, plus the original 125 kilojoules that you had to go over in order to get the reaction to happen in the first place when you were going from left to right. So you just add 216 to 125, which that's going to be 330, and 11 is 341 kilojoules per mole. Don't make the mistake of adding minus 216 here to plus 125 here. This one has to be taken, you have to take the absolute value of this, which would be plus 216 kilojoules per mole. Next slide. So here is your answer. You just add 216 to 125. Next slide. Which of the following, so now we're in Mr. Mack's AP Chemistry website, which again is just to give credit to that. And if you want, you know, once you get through the problems in this set, if you want, go there to his site and find this chapter, which is the one that's labeled kinetics, and just do something, because there's a whole lot of problems in there. as I said before, those actually in turn were taken from Brown and LeMay. So in some sense, we've come full cycle, right? But anyway, so if you want to do that, if you have time, I recommend that you do that. Just don't do too many of them. Just take them one at a time and make sure I understand this completely. And now I'm going to go on to the next one. Which of the following would not be acceptable units for a rate constant? Okay, so let's go through these together. So this would be the units you would have for a rate constant for a zero order reaction. And remember, for zero order, you don't have anything, so the K has to carry all the units, and we always want these units. For first order, we've already got the moles per liter, so we just need 1 over seconds, or it could also be 1 over minutes. For second order, we have too much. We have moles squared per liter squared. We need to get rid of one of the moles per liter, so we multiply by liter per mole, and that drops it back down to moles per liter per second. So that's going to be for 0. And then the next one is going to be for 1, and the next one is going to be for 2. And then the next one is going to be for 3, even though we didn't talk about that. And the last one's not going to be for anything, so this one is just wrong. It is not the units for anything, so the answer is going to be E here, because E is not acceptable units for a rate constant. All right, next. If it has units of liters squared per mole squared per second, that's going to be when you have a third order overall reaction and you're trying to get it to moles per liter per second. So if you have moles to the third per liters to the third, then for that you would have to multiply by liters to the second over moles to the second to get it back down to where you want it, which is going to be moles per liter. So our answer here is going to be for third order. Now, we didn't talk about these, and we're not going to talk about them, so you don't have to worry about it. The only time it comes up for us anyway is when you're talking about the overall reaction order, where you have 2 reactants, 1 second order and one's first order, and when you add them together, you get third order. Next slide. Next slide. Okay, this one I think is in here twice. Given the reaction NO plus 1/2 CO2 gives NOCl, and the following measurements. So these are kind of fun. They're like a puzzle. What rate law correctly describes this? I think we've already done this. And if we haven't, I think we'll do it again later. So here they switched it up and they put the rates over on the left. And here are the experiment numbers or the run numbers. All right, so we're looking for when we keep 2 things constant and change the other one. So here we're keeping Cl2 constant, we're changing NO. So if we do that, we're going to be figuring out what the exponent is for the NO. So we're doubling the NO from 0.5 to 1, so write down 2 as your base number, and the rate goes up by a factor of 4, which is 2 squared. So the order is 2. Now, if we had tripled it from 0.5 to 1.5, we would not have written 2 as our base number. We would have written 3. Anyway, the order for NO is 2. I think we've done this before. Now, when we hold NO constant and double Cl2, the rate doubles from 4.79 to 9.59. So we are increasing it by 2 to the power of 1. In other words, if we double this thing, we double the rate. So it's first order in Cl2. The overall action is going to be 2 plus 1, which is 3. All right, so the rate law will be rate equals some rate constant K times NO to the second times Cl2 to the first, which is answer choice D. Right? And let me just double check. Yeah. Okay, so it's answer D. Next slide. Next. Here's a reaction involving a pesticide. The rate constant is this. Here is a clue. You'll have to be careful and not miss these clues. So let's try to put a star there and a circle. What is the clue? So look at it for a second. The units are given in minutes to the -1. What order has units of minutes or seconds to the -1? Is it 0? No, because that would be moles per liter per second. Is it first? Yes, because first already has the moles per liter. So you just have to put in the seconds or minutes to the -1. So this is going to be first order. So let me just write a 1 here. The pesticide has an initial concentration. So this is your A0. And then AT is what they're asking. So that's our unknown. And T is 62 minutes. So notice they gave us the T and the K in the same units. They're both in minutes. Okay, so for first order, the for first order, the integrated rate law is logarithm of AT equals minus KT plus the logarithm of A0. We know A0, it's right here. We know t, it's right here, and we know k, it's right here. So we can figure out what the logarithm of AT is first by taking the logarithm of this number right here, and you'll have to get rid of the moles per liter and just take the logarithm of 0.0314. And remember, when you take the logarithm of a number less than 1, it's going to be negative. Anyway, so take that, multiply your k, 6.4 times 10 to the minus third, minutes to the minus 1, multiplied by 62 minutes. The minutes and the minutes to the minus 1 are going to cancel, and you're going to wind up with a number. And then multiply that by minus 1 because it's minus kt. And then add, but it's going to be a negative number, so you'll actually be subtracting whatever you get when you do the logarithm of 0.0314. And then that will give you not AT, but it will give you the logarithm of AT. And then all you'll have to do is raise both sides of the equation to e to the power of that side of the equation. And on the left, you'll get e to the logarithm of a, which will just reduce down to a. And then on the right, you'll have e to whatever the number is. So let's go to the next slide. So here is the rate law, the integrated rate law. We multiply the k times the time, take the logarithm of this, which is going to be a negative number. This multiplied by this times minus 1 is going to be a negative number. Add them together, and that gives us minus 3.86. That equals the logarithm of A2. At this point, raise both sides of that equation to e to the power of. So on the left, you've got e to the power of logarithm of AT, which is just AT, because the e and the logarithm cancel each other out. And on the right, you have e to the minus 3.86, or you can also write that as exponential of minus 3.86. And I just did it that way so you'd see that they're the same thing. So on your calculator, e to the minus 3.86 is 0.0211, and that is your answer, which matches answer choice E here. So that's our answer. Next slide. All right, NaCO, give NO plus 1/2 CO2 is a second order reaction. The initial concentration is 4.46 moles per liter. The reaction is half complete at 5.82 hours. When will it be 3/4 complete? This one is tricky. It's not hard, it's just tricky. So I'm drawing 3 lines here. This is the second order. So never mind, forget that line, I'm sorry. And actually, we can leave it there as kind of a marker. I'm drawing 3 lines here. So this is going to be when we're starting. I'm going to write S. And this is going to be after 1 half-life, and this is going to be after 2 half-lives. Okay, why did I make this space twice as big as the one before it? Because it's a second order reaction. So you'll have to remember this. For second order, every half-life is twice as long as the one before it. So, I mean, this one is like a certain distance between S and 1 half-life. And then, so the distance between 1 half-life and 2 half-lives should be twice as long. And they're telling us that this reaction is half complete at 5.82 hours. So what that means is that to be half complete, you had to use up half of what you started with. So if you started over here, let me write these numbers in. Let's say we started with 1 unit of whatever, then after 1 half-life, you have 1/2. So after 2 half-lives, you're going to use up half of this 1/2. In other words, you're going to use up 1/4. So now you're going to be down to 1/4 what you had originally. Another way that you could say this would be to say that this reaction is 3/4 of the way complete, because you only have 1/4 left of what you started with. So if you started with 1 mole per liter, you're down to 0.25 moles per liter at that last point. And that's what they're asking for in the question. When will it be 3/4 complete? Well, it'll be 3/4 complete after 1-2 half-lives. So for a second order reaction here, if the first half-life is 5.82, the second one will be twice 5.82, which would be 11.64. But you have to add them together because they want to know when will it be 3/4 of the way complete, starting at the beginning, which is over here. So you would have to add the 5.82 plus, let's see, that was 11.64 for the second one because it's twice the first one. So the total time for both the first half-life and the second half-life is going to be 11.64 plus 5.82, which is about 17.6 or something, or 17.5. Let's go to the next slide. Okay, and it is 17.5. So it's going to be answer choice E here. And so if you want to stop here and pause this and read it, you can. Otherwise, let's go ahead and move on. Next slide. This data, okay, so the data in the table below were obtained for this reaction. So I'm just going to do this one kind of quickly because we've done several like this already. So to try to keep the time on this video down a little bit, I'm just going to tell you what's going to happen. And so you'll want to go through it on your own. So what they're going to ask us is, what is the order for the ClO2? You can see that on this slide. Then on the next slide, they're going to ask us to do it for OH minus, and then also the total order. So let's do the ClO2 first. So we're changing ClO2 here, but they're doing it in a different direction. They're making it go from down to up, and we're keeping OH minus the same. And here, keeping the OH minus the same, and then what we're doing for the ClO2 is we're actually tripling it. So 3 is going to be our base number, and we're going to look at the rate and see what power would we have to raise 3 to get a corresponding increase in the rate. So look at the rates. You may want to take your calculator out and divide 0.0248 by 0.00276. But it's going up by a factor of 9. So I would have to raise 3 to the 2 power to get 9. So that means it's second order in ClO2. Then also, if you keep the ClO2 constant and triple the OH minus, the rate triples. Well, just for the sake of time, I'm just going to tell you the answer is going to be 1, and I had a 1 already inadvertently written there, but that wasn't a 1. That was just a marker. So let me mark out my markers. So we have a 2 for ClO2, and we have a 1 for OH minus. And then they're going to ask us what's the total reaction order, which is just 2 plus 1, which is 3. And having said that, let's go ahead. I'll let you look at these on your own. Let's move on. So next, 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 next. Okay, so here's a new problem. If the rate law for the reaction 2A plus 3B gives products is first order in A and second order in B, and you have to really pay attention here. Remember, we said that you cannot just look at that reaction and write the rate law. So here's how you write the rate law. They're telling you it's second order in B, so B has to be to the second power, and A has to be to the first power. So the rate law is rate equals KAB squared, which is answer choice E here. Now don't look at these coefficients and write rate equals KA squared B to the third, which is what they want you to do. So they give you that option to encourage you to go ahead and choose that one, but this one is not right. So again, the lesson here is, at least for our purposes for this chapter, is that unless we know it's an elementary step in a reaction mechanism, we cannot look at the rate law or find the rate law by just looking at the overall reaction. Next slide. Next slide. Here's one where they're giving us a graph. We have a straight line, so let's see what we're plotting. We're plotting logarithm. That means if we're getting a straight line, it's first order. I'm just going to write 1. And they told us that anyway. But it never hurts to practice. So CH3NC is going to CH3CN. That 3 there is not supposed to be there. There's a few typos in this stuff. So if it's first order, that implies that the slope is minus K. The slope is minus K. Or you could rewrite it as the K is minus the slope. Okay, so the rate constant here, let's see, now do they give us the slope? And it looks like they don't. So they don't give us the slope. So in order to find K, actually, let's do it this way. Let's say that K equals minus the slope, because that way we can just find the slope and then take the negative. So they didn't tell us the slope, so we have a problem, right? But we can figure it out. Slope is just the rise over the run, which in this case means the rise is going to be whatever you get when you subtract, it looks like about 3.5 from 5. So the second, actually it's going to be, the way I said it, you want to take the second point, which is going to be the one that happens later in time. So that's going to be 3.5 roughly, or maybe 3.45 minus 5. And I'm just reading those numbers right off the the y-axis here. So I'm reading this number is 5 because that's where actually that would be the first point, and then the last point would be here. And I'm reading that as, I think that's actually more like 3.45. Whoops, I got it too high. So right there. So it's going to be, but it's going to be 3.45 minus 5 because you want to take the second value minus the first value. So I know that's going to be negative, but it's a negative slope because the line's pointing down. So whatever you get when you subtract 3.45 minus 5 would be the rise, and then the run, or the part that goes in the denominator, would be just 30,000, right? Because we're going from time 0 to over here to time 30,000 seconds. So that's what would go on the bottom. So if you wrote that, the rise over the run, it's going to be 3.45, which I hate writing with this thing, which is why I don't do it that much. I mean, I could pick something like a piece of chalk on a chalkboard or a marker on a whiteboard, and I could write something about 10 times before I could write it out with this thing. So anyway, I mean, take a nap for a few minutes and then I'll wake you up when it's time to get up. So 3.45, and it's not 3.45, it's 3.45 minus 5. And so, yeah, that's going to be a negative number because 5 is bigger than 3.45. But anyway, whatever you get here, which is going to be about 1.5, right? It's actually, I think it's 1.55, negative 1.55 divided by 30,000. That is going to be the slope of the line. And then if you take the negative of that, you're going to have your rate constant. And that would actually be positive because since your slope is negative, if you take the negative of a negative, that's going to be a positive. So before we even go any more, we know it's going to have to be a positive. So we can eliminate answer choice D and A. And I mean, I don't think that C is even close. So I'm just going to guess it's going to be E, but let's look at it. So go to the next slide. So we get minus 1.55 over 30,000, and that should be 30,000. I don't know how that happened. And you get minus 5.2 E minus 5. So change it to plus, because the slope equals minus K, so change that to plus 5.2 E minus 5, which was answer choice E. Next slide. Okay, and then there are more problems there if you want to go to them. Next slide. A proposed mechanism for a reaction is slow step is the first step, and then they give 3 steps, and then they want us to write the rate law expected and what is the overall equation and what are the intermediates. So to do this, first of all, to do that last part, we add up everything on the left and everything on the right, and then we cancel everything that's on both sides, which let's just do that right now. We can see without even doing that we're going to have C4H9 plus on both sides. And also we're going to have this other thing with the plus sign on both sides because I saw that over here on the left. And let's see what else is going to cancel. Is that it? Yeah. So on the left we'll have C4H9Br plus 2H2O. Can you see that? I mean, without my writing it out and taking 15 minutes. So these things right here that I'm circling right now will be left over. So we'll have C4H9Br plus 2H2O. That's going to be on the left. And on the right, draw an arrow, and then on the right will be C4H9OH plus H3O plus Br minus. So that is going to be the overall balanced equation for the reaction. The intermediates are going to be those two things that I circle with the plus charges, C4H9 plus and C4H9OH2 plus. The rate law would be determined by looking at your slow step. So it's the rate equals some rate constant K times the concentration of C4H9Br here. And that's the only reactant, so it's the only thing that goes in the rate law. Next slide. So this is the same thing that we got for the overall balanced equation. This is the same thing that we got for the rate law. and the same thing that we got for the intermediates. So pause there if you want to. Next slide. All right, we have data here for the following three graphs. One of them is just concentration versus time. One's logarithm, so that would be for zero order if it was a straight line. Logarithm of the concentration versus time, so this would be for first order. And then 1 over the concentration versus time, this would be for second order. And it turns out here, which of the three is a straight line? Well, obviously that one is, right? So it turns out that what order would this reaction be? It would be second order. So the question is asking us what is the order of the reaction, and the answer would be 2. So let's just draw an arrow here. And then it also wants to know what the initial concentration of A is. That's at time 0. And you can do in math and science, you can do what's called extrapolation, where if you've got a straight line all the way up to the right-hand side there, you can just make the assumption it's going to continue straight down to right there. In other words, it's going to end up at about 10. However, be careful here because that y-axis is plotting 1 over the concentration. So what that's saying is that 1 over the concentration is 10. The concentration here of A, where if you look back at the top, A is the only reactant here. And again, you can just marvel at how long it takes me to draw this stuff out. 1 over A equals 10. So can you figure out what A would be if that's the case? So A would be what? 1/10, right? So the answer to part B here, the initial concentration of A would be 1/10 or 0.1. Next slide. All right, so for this one, I'm not going to spend a lot of time on it. What I did was I took these values that they gave you here. Let me just read the problem. The decomposition of hydrogen peroxide, H2O2, was studied, and we found the following data, which is given in this chart. And then assuming that the rate is the change in the H2O2 over change in time, find the rate law, the integrated rate law, and the value of the rate constant. Okay, so what I did was I plotted this data the way they have it here, which is just concentration versus time. And that's what we would expect to get a straight line for if we had zero order. But then I had to also change this by adding 2 more columns. One where I took the values that they have under the concentration here and took the logarithm of each of those, and that's kind of easy to do if you use the program called MS Excel or an equivalent program that's available in other proprietary softwares or other, actually it's available as freeware as well. And then I had to take 1 over that. And so what I did was I plotted each of those in turn versus the time. So I plotted this versus time, logarithm of those numbers versus time, and then the 1 over those numbers versus time to see if I got a straight line for any of them, and then I can come back and answer these questions. So let's go to the next slide. So here is the column they gave us, and then what I did, in Excel, what you can do is you can just, you can come over to an empty cell to the right here that has nothing in it and type in equals logarithm of whatever cell that happens to be, like say that's cell C3, then you could come over here and write equals logarithm of C3. You would actually have to put the C3 in parentheses, and it will give you that, and then you can just drag that down by clicking at the bottom right-hand corner of that cell, which I can't get this thing to write now, and then drag down, and all of the other values change automatically. So it's incredibly powerful. And then do the same thing, just do equals 1 over the C3, and you get 1 over 1 is 1, and then come to the bottom right-hand corner and drag down again. Okay, so once you've done that, then you want to make 3 graphs. One where you're plotting this versus time, one this versus time, and one that's this versus time, which is done on the following slides. So let's very quickly go to that. So this is what I got when I just plotted the basic concentration versus time. And this is not a straight line, as you can clearly see. When I did logarithm concentration versus time, I got this, which looks very much like a straight line, right? And then when I did 1 over the concentration versus time, I clearly, again, didn't get a straight line. So it's very clear that the logarithm of concentration versus time is the one that gave the straight line, and that means it's a first order reaction. So having said that, that means that the rate is going to be some rate constant K times the concentration of the reactant raised to the first power. And then you can just remove that 1 there because it's implied anyway. So the rate is just the constant times H2O2's concentration. The integrated rate law, we only have one reactant, so the logarithm of its concentration after time t will be minus kT, which we could figure out what the K is, and we do that in a minute, plus the logarithm of the H2O2 concentration at the beginning. To find K, we can actually choose any of those rows of data, find the H2O2 concentrations here, and then we know what the time would be. So you would have to take one line of data to be your first time, and then another line of data would be after some time t has gone by. So if you'll, I can't go backwards, but if you'll go back, if you're interested, you can go back and look at the data at the beginning of the problem. And what you could do is take, for example, the first line where you're starting at, t0 or whatever, and then find the amount of time that elapses between that and either the second row or the third row or whatever row you choose, and then see what happens to the concentrations. And then just substitute in the values. This would be the first concentration in the line above, and this would be the second concentration. And then the time would be the time that's elapsed between those two lines, and just substitute those in. And I've done that here. So for example, I did, this was the first line and this was the second line. So I just put in those concentrations. I just read them right out of the chart, and then the time that had elapsed was 120 seconds. So I take logarithm of 1 minus logarithm of 0.91, divide it by 120 seconds, and that gives me my K. It's just algebra, and you get that K is 7.86 times 10 to the minus 4th seconds to the minus 1. And then they wanted us to figure out what the concentration would be after 4,000 seconds. So again, you use this equation, this integrated rate law here. And now you know what K is because you figured it out here. And they give you the time, so you know what K is, you know what the time is. And for that last part, 4,000 seconds, and then we're assuming that the concentration here at the beginning was 1, so the logarithm of 1 is 0, so that whole term vanishes. Next slide. And then this is another way you can do that same problem that the book uses, which is different. So if you want to look at that, you can. Next slide. All right, so that wraps up chapter 14. This is about the amount of time I'd like to spend on the work problem sets, although you can't always do that. But 45 minutes is about right for a set of work problems. So let's stop, and I'll see you in chapter 15.